All right, hello everyone. Welcome to the third part of the video for section 4.7. I just want to go over one more example of an applied optimization problem that will hopefully be helpful for you as you approach your homework problems. And again, I want to reiterate that you hopefully have started the homework problems for this section already. Again, they are quite challenging, so please make sure that you start on those right away because they do take some time. Okay. I also hope you take some time to admire this meme because it is one of my favorites. Okay, so let's look at this problem. And again, this is one of those that is stated in one line, but can take a little bit of time to figure out. So the first thing, or what we're looking to do here, is find the point on the line y equals 12 minus x that is closest to the point 4, 2. Holy buckets. What the hay is going on here? Okay, so first things first, just as we've done with a lot of these questions, let's draw a picture. So I will not do that, but draw a picture like this. Here we go. So here are my coordinate axes. I'll go ahead and put my arrows on the ends here. Okay, I'm going to draw that line y equals 12 minus x. Now when I do that, I know that in this case it's going to be a line that slopes down from left to right, and it's going to intersect the vertical axis at 12. So I'm going to put that here. So here's 12, and then the line will look something like this. Okay. So that's going to be our line y equals 12 minus x. And then we're trying to figure out the closest point to the point 4, 2. So let me put that in here. So 4, 2 probably be somewhere around here. Okay. So let me label that. All right. Now, if it's the point that is closest to that, first of all, let's think about what that means. So it wouldn't be a point like over here, or say over here, because that's definitely not closest. So it's probably going to be a point somewhere along this, right around there. And if it's closest, what does that mean? Well, that means the distance between the point 4, 2 and that point there on the line is going to be the smallest possible, right? Because notice if I go to either of these other 2 points, this one or this one, they are further away, so it's going to be the one that is closest. And as I said, we measure that in distance, and I am emphasizing that word distance because we probably need to use what formula here? Right, the distance formula. And you may recall the distance formula is given by d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay. Now, the point we are looking for, we don't know the coordinates of, right? It's this point that I've highlighted right here. Okay, but we do know something about the coordinates of there. We know it's going to be an x and a y. And in fact, because it is on this line 12 minus x, we can be more specific in that the coordinates there are going to be x comma 12 minus x, right? Once you have the value for x, you plug that into 12 minus that, and it gives you the value for y. Okay, well, using that together with the coordinates of the other point, we can at least write an expression for the distance between these 2 points. So that would be d equals the square root. I'm going to use these here as my x2 and y2. This will be my x1, y1. So I'll end up with x minus 4 squared. That's supposed to be a 4. Plus 12 minus x minus 2 squared. And let's see, we can do some foiling there. So foil out the things that are squared, or actually, first of all, simplify on the inside. We have a 12 and a minus 2 there. Foil some stuff out, combine like terms. And when we do that, I believe what we end up with is square root, and not in red though, square root of 2x squared minus 10x plus 116. And you can double check me on that. Make sure I didn't make any errors. Okay, and so that's our expression for the distance. And we're trying to find the point that is closest, which means we need to minimize this, right? And we know that generally for these types of problems, the next thing to do would be to take the derivative. However, taking the derivative here is going to be real nasty because there's this square root. And so what we can do to deal with this, getting rid of the square root, is actually square both sides. So we end up with d squared equals 2x squared minus 10x plus 116. And it turns out that if we can find a minimum value for this, that gives us a minimum value for the thing with the square root, which might be kind of surprising, but it's true. So I'm going to call this value capital D now instead of d squared, just to simplify things. So we have d equals 2x squared minus 10x plus 116. Take our derivative here, we get d prime equals 4x minus 10. Set that equal to 0. And when we solve that, we end up with x equals 10 over 4, or 5/2. Okay. Now, one thing we didn't do on this problem that we have done on the others is put a bound on the value for x, which we could have done. But instead, in this case, let's just check to make sure that this is a actual place where a minimum occurs. And so I will draw my number line here, put 5/2 on it. Okay, where we know the derivative is equal to 0. Plug in a point on each side to the derivative, so I could plug in, say, 2 and 3. And when I do that, it looks like the value of the derivative is negative over here and positive over here. So what we see is that we do, in fact, have a local minimum there. So we know this value of x does give us that minimum distance. And again, let's double check. Have we finished this problem yet? We're asked to find the point on that line, right? Well, just finding x equals 5/2 does not complete that part of the task, right? What else do we need to do? We need to find a value for y. So we could do y equals 12 minus 5/2, which would be like 24 over 2 minus 5/2. So it looks like we'd get 19 over 2 there. So we know then that our point is, that minimizes the distance, is 5/2, 19/2. Okay, and there we go. All right, that's all for now. Thank you for watching.